what is the need of normalization? After all, what a normalization is? Well, the normalization is needed to reduce redundancy. What do we mean by redundancy? The basic objective here is, whenever we are inputting information into a database management system, in all likelihood we may end up creating tables which may have redundant information. Well, that doesn't sound to be true. It's not very clear from the statement. It will be clear only if we look into the examples of this kind of a thing. The second main objective of normalization happens to be that we want no loss of information from the database over the lifetime of the database. What do I mean by loss of information? Well, you will find this particular term more clear when we talk about the example of a relational database design. Well, it may not be the design issue which we are discussing or we are trying to discuss here. It is mainly we are trying to define a student's relation, and without this particular example, the discussion which we are going to make will be incomplete. Now, if I want to define a student relation, what are the attributes which I would like to define for that particular relation? Well, we cannot show all the attributes in a given environment, so we have chosen some samples. Those are, in a student relations, the name, the course, the phone number, the major, the professor, and the grade. I repeat, in the student relation, we have chosen the name, the course, the phone number, major, professor, and grade. After all, what these terms mean? What are these attributes? Obviously, the name specifies the name of the student, course, definitely the courses which he has undertaken, phone number specifies his phone number, major, for example, computer science can be a major, other majors can be, there may be mathematics, physics, those kinds of majors. Then professor, who has taught a student a given course, and definitely the grade specifies what grade he has obtained in that particular course. Now, coming back to the basic thing, if I am designing a database, these are the fields or attributes of that particular database. What I would like to do with this particular database? Are there any constraints? Are there any assumptions associated with this database technology or this database management system, or in fact for this particular database? Well, there are several constraints which we have identified in general, which may be applicable to the given set of conditions or given database. The constraints are, the very first constraint is that we want that the student name should be unique. In addition, we also want that a student can join many courses. Yes, that is the realistic situation. A student can have one phone only. A student can take major in one subject. A course is taught by only one professor, and one grade is given to the student for a particular course. What do I mean by all these constraints? After all, these constraints are trying to pinpoint or restrict the design of my database management system. But these kinds of considerations does exist in a realistic or real life situation. So keeping these constraints in mind, I have to design my database management system. Now let us look at the relation state, keeping those constraints in mind which we have said right now. Now the state of the relation can be defined as the instance in which the database is currently. For example, you can see in the slide there are almost 7 or 8 records which are being entered at a particular instant of time. It may be changing over a period of time. More students will be joining, more courses will be being offered by the university, and so on and so forth. But look into some specific things which are there in the slide. The very first thing is that there are several names listed. These names, okay, they are repeating in the table at several places. Okay, for example, Rohit, okay, which is appearing here, here, as well as here. Okay, please note one particular thing. According to the constraint, the database or the state of the database should be in consistent state, in the sense that if the name of Rohit is appearing twice, it will not be appearing for the same course. It will be appearing for 3 different courses in this particular table. The other constraint was that one course is taught by one particular professor. So try to see this particular point also, that a course CS 303, which is appearing twice, is being taught by a teacher or Professor Bharat. Similarly, what you are going to find is that wherever Rohit is appearing, the phone numbers as well as the major remains in consistent state. What we are trying to say here is, whenever we are trying to find out the state of the database, we are trying to see some of the constraints are implemented properly and database is in consistent state and it is not violating any of the integrity or any other constraint. If that is what we want, what we would like to see is that there is no redundancy in the database. Why do we like to see that there is no redundancy in the database? Obviously, there are going to be certain reasons associated with it. The very first problem which we are going to encounter in the table which we have designed is the problem of redundancy. Now, what is that particular problem? I think let us look at the table once again. The problem of redundancy which can be visualized here is that Rohit's telephone number is appearing many a times. His major is appearing many a times. Similarly, the course CS 303, the professor who is teaching that particular course is appearing twice. Now, this is redundancy in this particular table. The second problem which we are encountering in this particular table is there are update anomalies. Now, what is update anomalies? What do we mean by having update anomalies? Well, I want to update the telephone number of the student Rohit in my table. If I want to do that, there are 3 places where the telephone number is appearing, and even if by any chance I miss one of those instances, then it is going to create lot of problem as far as information is concerned. Okay? So, this is one particular thing which you really have to see here. Okay? If that is so, okay. So, let us look into the second problem. The second problem is insertion anomaly. What do I mean by insertion anomaly? Well, if I want to put or if I want to insert some information into my table, okay, what will happen with it? Probably, let's take an example of the same table. Let's say a course CS 500 is to be offered by Professor, let's say Shyam or Professor Ram. He wants to offer a course CS 500 which is not existing in that particular table. However, in this table I cannot store that information. You understand? Why can't I store in this particular table? Because no student has taken that particular course as yet, I want to float that course, but no student has enrolled in it, and I cannot enter that information into this particular table. This is insertion anomaly. Why can't I enter this particular information? Once again, the integrity constraint forces us to do so. Why integrity constraint forces us to do so? After all, you see, the key for the relation which we are considering is, the key happens to be the name as well as the course. So this is one problem which we are going to encounter here. So these two things, that is name and course, combined together should formulate the key to this particular relation. Okay? So this is why I cannot enter the information without a student taking that particular course, right? So this is insertion anomaly. What about a deletion anomaly? What do I mean by deletion? Well, what happens, let's assume in the same table, the course CS203, okay, which is taken up only by Mr. Rohit, okay. So course CS203 is only with Mr. Rohit, and he wants to drop, in fact he cannot drop this course because he has already obtained it, but let's say Martin, who has taken CS503, and he wants to drop this particular course which is in progress. Unfortunately, in this particular case, what will happen? In this particular case, the information that CS503 is being taught by somebody, a professor, will be lost along with this particular information that he wants to drop this particular course. Therefore, what we visualize is that in a relational environment or a relational database management system, we are going to encounter lot of problems if we do not properly design the database properly and correctly. But if I want to do so, do I need to know something else before I start designing the database management system or database scheme? Well, in that particular respect, one term which is most important is called functional dependence. What is functional dependence? In fact, the functional dependence is defined to be the constraints on a legal relation. So whatever constraints which we had defined earlier basically should be translated into the term of functional dependencies. In addition, functional dependencies express facts about the enterprise that we are modeling with the database. In fact, this is just an elaboration onto the previous point. The previous points was saying that these are constraints and elaborating in the sense that the constraints which are there in the model itself. Okay. So what we are basically saying, functional dependencies are real life constraints which are normally put onto the database management system by the modeling environment or somebody else. But how do I identify functional dependence? How do I go for that? Well, there is no algorithmic method of identifying dependency. We have to use common sense and judgment. So that is what it is. Functional dependencies need to be identified by us, by you, based on the model which is being offered by a particular person for whom you are designing the database, and you will be implementing it in the required database management system. Well, so this is what we have talked about. We have a student database management system. We have defined the constraint, but that is functional dependencies. But what is the implication of these functional dependencies? Are we going to use them somewhere? Well, the very first thing which we would like to do in our relational database design is we would like to represent our functional dependencies in the form of a diagram called functional diagram or dependency diagram. Please look into this particular diagram. What we have an attribute called name and course. Name is uniquely identifying phone. So if I fix name, for example, so and so, Rajiv, Rajat, or anybody, his telephone number also gets defined. He has just one telephone number, so it is clear to us what number we are talking about. But the first thing is his name should be defined. Over here, what we are assuming, that names are unique. In certain cases, you will say that names may not be unique. In those cases, your enrollment number can replace the name as far as key is concerned, okay, or the defining attribute is concerned, right? So in this particular environment, let us continue with the name, and we are assuming the names to be unique as defined by us in the very first instance. Well, so what does name specify? Name indicates the phone as well as major. This is shown by the arrows. So I fix up the name, his phone number and major can be determined. I fix up a course. Since a course is being taught by only one teacher, I can always determine who is the teacher who is teaching this particular course, that is the professor, okay. And lastly, if I fix up the name as well as course, only then I will be able to tell about the grade. Now that is important. There is one attribute which is dependent on the combination or composite attributes which is happening to be in this particular relation to be key attribute, okay. So this is the functional dependence diagram in the given situation. But what do we do with this particular dependence diagram? What is the significance of it? But before I want to know significance of it, the next question which comes to me is, I have said that there is a database, it is anomalous, there are problems in that particular database, problems relating to redundancy which leads to many other problems, okay. How do I resolve those problems? Okay, those problems are to be resolved using the method of decomposition. That means I would like to decompose the student relational scheme into smaller tables or relations. Database being the student, however, I would like to decompose it into smaller relations. Will this smaller relation solve this particular problem, and how FDs are going to help us in that? That is one question which we would like to answer. But prior to it, if I want to decompose, what are the characteristics of decomposition, or what should be the basic facts which I should encounter in the decomposed relation? Well, the desirable properties of decomposition are happening to be lossless join decomposition. That is, on taking join of the decomposed relations, we should have the same set of tuples as originally we started with. It is basically saying that if I combine, now how do I combine? Using the join operation. That means there has to be some attribute in the decomposed relations which will be able to join the relations and should be able to produce the original relation, that is the original relational state. So if I start with the state, I decompose it into a relation and define the state of those two smaller relations, I should be able to get back the original tuples. If I am not able to get those, then it is a lossy decomposition, and I would never like to have lossy decomposition. Okay. What is the second thing which I would like to, or desirable property? That is dependency preservation. Okay. That I would like to preserve the dependency. That is, what do I mean by saying so? That the constraints should not be violated. Okay. So, what is the basic objective? The dependency represents constraint, and my decomposition should ensure that these constraints are not violated. Probably this is one situation which we cannot meet always in some of the normal forms. However, this is one of the most desirable property of a decomposition. So, now the question comes, will normalization help in these activities? Well, the normalization is an attempt to eliminate or minimize the problems occurring due to data redundancy over the lifetime of the database. Lifetime we have specified because we are talking in terms of states of the database. And the second point is normalization is an attempt for good database design, and it involves decomposition. So, what effectively we are doing normalization for? We are trying to decompose the relation using the standard principle or defined principles of normalization. Okay. So, if we have certain defined principles of normalization, which should be definite sets of rules, there has to be certain definitions for those. So, let us try to understand various normal forms which exist for database design. In that particular category, the first definition is first normal form. The first normal form is defined to be, it is also called a flat file and is shown as 1NF. There are no composite attributes and describes one property. What do I mean by? The basic thing which we are meaning by this is that all attributes are single attributes. They are not multi attributes. One multiple attributes can be address, which consists of house number, then state, territory, and so many other things, including pin code. So, that is a composite attribute. If that kind of a composite attribute is there, probably it is to be broken down into single attributes. So, in first normal form, actually we convert whatever information is there into a proper table. Another thing which we are saying here is a database scheme is in 1NF if every relation scheme included in the database scheme is in 1NF. This is in the context whenever we are talking about a database management system, there may be several relations or tables existing in that particular database. Okay. So, if we are talking about 1NF for a database scheme, we must ensure that all such relations are in 1NF. The example which we had shown to you earlier, okay, that is in 1NF. The student database is in 1NF. It is a proper defined table. Okay. So, this is an example of 1NF. Fine. So, if we have already designed our table or our database into the first normal form. But in this particular first normal form, as indicated, there are problems. The problems of redundancies, the problem of insertion anomalies, deletion anomalies. Okay. So, these problems are definitely there into this particular relation. How to eliminate these problems? For that, a set of rules have been defined in the terms which we say second normal form. We will be progressing on that. The second normal form is a relation is said to be in 2NF if it is in 1NF and non-key attributes are fully functionally dependent on the key attributes. What does this mean? Anyway, we will talk about it. The second point here is if the key has more than one attribute, then no non-key attribute should be functionally dependent on part of the key. This also has certain meaning. So, let us explore their meanings with the help of functional dependency diagram which we had created earlier for our given relation. The 2NF statement basically imply that this happens to be the key attribute in our relation. It implies that all these attributes, okay, should be totally dependent on the key attributes. In a sense, grade is a proper, this particular attribute is being properly represented because name and course determines the grade. However, phone, major, depends on part key, that is name. Professor depends on course, which is once again part of the key. And this particular dependence, in fact, has led to the problem which we had seen earlier, that is insertion anomalies, deletion anomalies, and redundancy of information. How can we solve this problem? The basic logical solution which comes to our mind is we can solve this problem by decomposing. How do we decompose? Yes, the decomposition can be viewed from the slide once again. For decomposition, what the most logical thing to do will be, I create a table with name, phone, and major. That should be able to solve the problem, okay, on one sense, because we don't have to repeat that is phone number and major whenever a tuple is to be added for a different course. Okay. Similarly, in all the places, what we are doing for a course, necessarily we are entering information about the professor. Okay. So a course may be taught by one professor, however many students can take that particular course. So this information will also be repeated in our unnormalized relation. So the next possibility will be that we break course and professor into another relation. Okay. And third one, definitely, which is satisfying the constraints, is that we have name, course, and grade as the third relation. So in a sense, what we are saying, that we have to decompose this particular table into three relations, and these three relations, if kept separately, the problems relating to non-normalization are not going to exist. And these three relations are the student info, which consists of name, phone, and major; result, which consists of name, course, and grade; and course teacher, which consists of course and the professor. So by decomposing into two normal form, we are getting a very right or decomposition, we are getting the proper decomposition, and you can test that, you can test it by whatever data values are there, you can put those data values accordingly, project them into the new tables, and you will find, on taking the join of these three relations on various attributes which are combining the two, you will find that you will get the same original relation. Okay. As far as dependencies are concerned, you will find that all those dependencies are being preserved. What do I mean by dependencies are being preserved? You will see this particular, that is name to phone dependency, name to major dependency, is being preserved into the first relation. Course to, that is name and course to grade, is being preserved into the second relation which we have designed, decomposed relation, as well as course to professor is being preserved into the third relation. So this is the way we have designed the proper form of this particular database. But is it the end of the story? So thus we conclude that by two normal form, the whole theory of normalization finishes or completes, or there are still more problems? Well, for the time being, for this particular example which we have taken, probably the problems are over. Okay, but this may not be in general the case. What kind of cases which may exist? Let us consider the relation which is given in the graphics. Well, visualize the relation, the roll numbers, the name, department, year and hostel. Once again a student database for a person whose name is Raman, physics, etc., etc. The data is there. He is in the first year and he is allocated to a hostel called Ganga. Okay. Similarly, he is in the second year, he has been allocated Kaveri, third year Krishna, fourth year Godavari. Well, this highlights some point. Roll number uniquely identifies, or roll number functionally determines the name, roll number functionally determines the department, roll number functionally determines the year as well as hostel. So that is perfectly okay. Okay. That means the given relation should be in 2NF. There is no problem. 2NF, as we said in the earlier case, there were no problems in the 2NF relation, but is there any additional constraint we can see in this particular state? Well, in the graphics, if what we were pointing out, that if you are in the first year, you are in Ganga hostel. If you are in the second year, you are in the Kaveri hostel. In the third year, you are getting Krishna, in the fourth Godavari. That means something. A non-key attribute here can determine which hostel the students will be residing. That means there is a dependence existing between the year as well as the hostel. To visualize it, let us look into the dependency diagram. Now, dependency diagram states there is a link or there is a functional dependence from year to the hostel. If that is so, we are in trouble. Why we are in trouble? As you have found in the table, in the diagram which I had shown to you, wherever we are having one Ganga, it is being repeated. Ganga is being repeated. Whereas, if I simply say one, it should be sufficient to say that he will be residing in Ganga. There are inconsistencies. Not inconsistencies, there are redundancies, and obviously it is going to lead to the problems relating to insertion anomalies and deletion anomalies. To avoid such kinds of things, what we need to say, we need to go to third normal form. What is third normal form? The third normal form is defined to be that a relation should be in 2NF and all attributes in a relation scheme are functionally dependent only on the key. So, what constraint we are adding here? We are adding one more constraint here, and that is that it should be only dependent on the key attributes, and then only it will be 3NF. Obviously, we are moving from 2 to 3NF for the reasons, once again, that is anomalies, that is insertion and deletion and data redundancy problem. In 3NF, what kind of a decomposition will I get? Obviously, what I would like to break year as well as hostel into a separate relation, whereas roll number, name, department and year will be kept in another relation, and that is going to eliminate the problem which is associated with this particular table. So, in 3NF, what we are trying to do? We are trying to eliminate any attribute that is non-key attribute related functional dependence. So, you can see functional dependence is one of the prime factor which is responsible for this particular decompositions. But is BCNF that is 3NF sufficient, or we still have to move further? Well, 3NF to certain extent may be sufficient. However, a more rigid and defined form for 3NF happens to be BCNF, and in BCNF the basic assumptions are that the relation has more than one composite candidate keys having one common attribute, and if there is such case, then if not common attributes of one composite key is dependent on an attribute of other composite key. A normalization called BCNF is needed. So what we are saying, in 3NF we are removing some problem, that is non-prime or non-prime attribute related problem, but the problem can exist because of prime attributes also. That is, if we have two candidate keys, one is a part of, that is non-overlapping part of those candidate keys is functionally determining the other part. Since they are not falling into the that is prime attributes, then you are going to encounter that these particular relations are in 3NF, okay, but they are not going to be in BCNF. Let us explain it with the help of an example where we are visualizing a professor database, where professor code, department, head of department and present time is there. Now, some of the basic assumptions which are listed happen to be a professor can work in more than one department. Okay. The percentage time he spends in each department is known and is defined, and each department has only one head of department. So, these are some of the constraints which we are defining. If these are the constraints, obviously all these constraints we would like to represent with the help of a dependency diagram. Now, the dependency diagram is what we should like to see here. The department, the whole key. Now, these onto the left hand side which you are seeing here, these are all key attributes, although there are two candidate keys. The first candidate key is department and professor number, and the second candidate key is professor number and HOD. Okay. If we consider department and professor number, they uniquely define the percentage time. If we consider professor number as well as HOD, they also uniquely define the percentage time attribute. But in addition, what we are having is a dependence at this point of time. That is, if I know a department, I know who is the HOD. In a sense, department functionally determines the head of the department. If that is so, we are going to fall into some problem. What is going to be the problem? Once again, you will see wherever. Okay, so a professor may be occurring at various places. Okay, he may be in 2 department, 3 department. Okay, and there will be many professors in those departments. In all those places, in this particular relation, we are going to find redundancy of information as far as department and HOD fields are concerned. They are going to be repeated. Obviously, one of these fields should be kept, but you are going to, both the fields are going to lead to redundancy. And obviously, this is once again going to lead to the problem of insertion anomaly and deletion anomaly, and once again what we have to do is decomposition, and this is what the decomposition happens to be. Professor code, department and percentage time is kept into one relation, and we separate out department and HOD. So, by this particular decomposition, what we are basically trying to ensure that our relation is in BCNF and we are divided, or we are not having the problems associated with redundancy, insertion anomaly as well as deletion anomaly. So, we have reached to a state where we say, okay, the relation is in BCNF, but does it exhaust all possible combination of realistic or industrial situation? Probably we have some more examples to see. One such example happens to be the example of a course relation. The course relation, we are, for simplification, we are just considering 3 attributes: course, teacher and text. Okay. What we are assuming here is that a course can be taught by many teachers, okay, and the teacher can teach multiple courses. That's slightly different issue right now, but whosoever teaches a course has to use specified number of text irrespective of whosoever is or whatever teacher is teaching that particular course. In this particular case, the information which we would like to represent in this particular table basically is, we have given an example of just two courses. Suppose I want to represent information CST 203. The two teachers are happening to be date and Koth, and the two texts which are to be taught in this particular course are happening to be file organization and relational design. CST 103, we have Sahani, who is teaching this particular course, and he is also teaching file organization and trees. This kind of overlap in text is possible among different courses. That kind of a thing does exist in a real life situation. Now, how would I like to represent this information into the tabular form? Well, I have to represent this information as shown in the diagram, that is, for date, for each text, okay, for each teacher I need to represent. For example, CST 203 is being taught by date, okay, is being represented with two tuples and not one tuple. Here what we have to do is that CST 203 date file organization. So the information is like this: course CST 203 is being taught by date and he is teaching the text file organization. CST 203 is being taught by date and he has also to teach relational design. Similarly, two tuples are there for Koth. Similarly, two tuples are there for Sahani. Okay? As many texts are going to be there, as many tuples are necessarily to be entered. If we don't enter them, then the possible implication of the information may be, for example, if I don't enter that date with relational design, okay, that CST 203 date is teaching relational design. If I don't enter this particular tuple, there can be misinformation that date is just teaching the file organization. Okay, so this particular misinformation we cannot give. What we are trying to say here is we have the same problems once again. Okay, the FD is constraints. There is no FD in this particular relation. Why there is no FD? You will find that the whole, that is course, teacher as well as text, all of them combined together forms the key. So if these are the three candidate, the attributes of, or the key, the prime attributes, then there is no chance of having any functional dependence into this particular relation. If there is no functional dependence, obviously this particular relation is in BCNF, yet it has the problem of redundancy of information. Why the problem is occurring here? The problem is occurring because of the independent nature of teacher as well as text. So what we would like to do? Our common sense says that I would like to decompose this particular relation into a form called fourth normal form, okay, and the two relations which should exist here should be course and teacher. Okay, a course defining various teacher, I can uniquely represent the information, and course and text. Okay, so by this I can decompose the relation. What is the basic theory behind this particular decomposition? The basic theory for this particular decomposition happens to be defined as multi-valued dependencies, and that multi-valued dependencies is the prime factor for defining or using fourth normal form in a relational scheme. What is a multi-valued dependence? We have given just example of it. If I say course multi-determines teacher, that is if and only if the set of teacher value matching a given course text pair values depends on only course and not the text values. The independence which I was talking about, that is, if I know the course, there are multiple teachers who are teaching it which are independent of the text which are there. Okay? So, this is what this particular statement means. Okay? And the second statement which is there is that course determines teacher also implies that course multi-determines text should also apply in the given relation. So, what we have is these kinds of dependencies, and on that basis the decomposition as I had proposed has to take place. That is, we are going to decompose the relation into course teacher and course text. But is it complete? No, we still have one more problem probably. Now, how that particular problem can be visualized is a situation. Let us consider a vendor supplying many items to project in an organization. Now, what are the constraints in that? A vendor can supply many items, a project can use many items, and a vendor can supply to many projects. An item may be supplied by many vendors. If that is the situation, what we are visualizing here is a case where all these attributes, that is the vendor, the items which he supplies and the projects, they are independent of each other. Once again, in this particular case, what you are going to find that since they are independent of each other, they will not be in any sense being controlled by each other. Therefore, joining these the key will be consisting of vendor code, item code as well as project code. Okay? So, the composite of these three things will be the key. There is no functional dependence, so the relation is in BCNF. There is no MVD also existing in this particular relation, therefore, it is in 4NF2. However, if I want to decompose this particular relation into 4NF, into two tables, okay? After all, what is the problem in this particular table? Once again the same problem. If I want to represent the information that this vendor supplied this particular item, okay, and if he is not supplying that item to any of the projects, then this information cannot be represented in the table shown in the diagram. Okay. I cannot represent that V3 is supplying item I1, okay, to P2. In fact, there is a duplication that must be treated as a mistake. There is a duplication of information. Just one of these tuple is going to remain. Not the two tuples are not going to be there. But visualize it. V3 is supplying item I1 to project P2. Vendor V2 is supplying item I3 to project P1. But suppose he is not supplying it to project P1, then once again we are going to encounter the similar kinds of anomalies that is we had encountered earlier. Obviously, we would like to break it into two tables, okay? But those two tables which we can I mean, after all, this is not MVDs there. So, obviously, those two tables which we would like to define here are happening to be vendor code, item code table and vendor code project number table. However, what we find on taking the join of these two tables, the original table we will not be able to make. This is what you have to experiment. So, if you are not able to make the original table, what is the solution? So, under the circumstances, what is to be done in this particular case? Obviously, we would like to see that this particular table is not too decomposable, and this particular problem can be refined or can be implemented, okay, using multi-decomposability nature of these particular table. That is, instead of 2 tables, if we can break this particular relation into 3 tables by representing the third piece of information, that is, that which item is needed or used in which project, if we can provide that information also in another table, probably we are doing the proper justice to this particular table. These kinds of the normalization is called 5NF. Okay? And 5NF is basically based on something called join dependency. That is, on taking the join of the 3 table, I'll get the original table. On taking join of the 2 table, I will not get the original table, and that is a problem. So we have broken this particular relation into 3 tables. Okay? So that tells us about the fifth normal form. Now let us summarize what we have done as far as normalization is concerned. In normalizations, all relations, if I want to a non-normalized relation, if I want to convert it to 1NF, I have to eliminate variable length records, multi-attribute records. Okay? If I want to convert 1NF relation to 2NF, I have to remove dependency of non-key attributes on part of a multi-attribute key. Okay? If I want to convert 2NF to 3NF, I have to remove dependency on non-key attributes on other non-key attributes. If I want to convert it into 4NF, or in fact 3NF to BCNF, then I have to see the removal of dependencies on attribute of a that is, whenever we have multi-attribute key, that if there is overlapping onto the non-overlapping portion, there shouldn't be any redundancy or any dependency. In 4NF, what we try to remove is multi-valued dependencies. So if I remove all the multi-valued dependencies from a relation, I will bring my relation to 4NF. And finally, to convert a relation into 5NF, I need to check whether a given relation is a 2 decomposable, or it requires more relations which can be joined together to bring the original relation. In practice, you will find that this 5NF is not very commonly used. However, you will find that there are practical instances existing for 4NF as well as 5NF situations. The other part which you would like to see here is the query processing. What I will request you, you must try to experiment with lots of queries. You may take exemplar queries from the references books which we have suggested to you, and try to experiment with some of the queries, try to design your own queries, and that will give you tremendous confidence as far as query optimization is concerned. In fact, query optimization will come as a next step if you have designed your queries properly. You must try to, you should try to solve many queries using join and other similar kinds of concept which you have learned in block 1 as well as block 2. With this, I would like to end this particular session here. Bye, and thank you for listening to me.